Alright, we're going to introduce 2D vectors and then quickly move into 3D vectors as we go forward here. So the big idea behind a vector is it has a magnitude, which is just a size, and it has a direction, which is going to be an angle. And we have scalar quantities, which are just values, right? So time, speed. Speed doesn't have a direction. Volume is just a quantity, right? There's no direction attached to that. A position vector is something where it starts at the origin. So at 0, 0, it's called a position vector. And a displacement vector is the difference. So it's going to be our subtraction between an object's initial and final position. And we'll use those as we go forward here. But the big idea is a vector, size and direction. We have scalar values. We have a position vector, starts the origin. And then displacement vector is a subtraction. And so if we look at these as we move forward, all right, there's vector A. We can move vectors around, so I can pick them up and move them. That's an equivalent vector. And if we are going to add these two vectors, we add head to tail. And so my resultant vector, what results, is this blue one here. So I can imagine I push a particle here and then I push it there. That's the resultant. That's where it actually ends up. If I take some vectors and subtract them, that's my displacement vector, right? I'm just, in this case, going in this direction. So that's A minus B. I could think about if I flipped one of these vectors, so let's say I made the opposite of B, and then I moved vector A around, so I would have minus B, and I can pick it up and move it with my values, and I would get an equivalent piece there, and I can see that these two are the same. So it's the same idea as adding a negative B. Alright, so we're going to move into some calculations with our components, and the big idea is we have components which are I hat and j hat. This is a unit vector, a length of 1 across in the x direction. This is a unit vector of length of 1 in the y direction. And so if we want to add values and we have components, we just take the two components and add them together. So we can see that we have a 4 and a 6. Those would add to 6 i's. That's equivalent to 6 i's. And then we do the same thing with our j's. So we can run through these quickly. The opposite of b is we just flip the signs on the components. A minus B, I subtract the components. I want to make sure to subtract the whole thing, and then I get my values, and then we have another piece here, so this would be if I was subtracting them, right? I have my values. I can think about the magnitude of those, okay? The magnitude of those is specified with these vertical lines, and that's just basically the length. That's the size of our vector. And the Pythagorean theorem is going to be your friend as we move forward with that. If we look at the direction, we would want to use a little trigonometry. We could take a tangent inverse of our ratio, right? This is 11, this is 2, opposite, adjacent, gives us our direction for a tangent. If we subtract these, again, it's the same idea. We just make sure that we have the right vector in the right spot. We get our values, and if I want to find the magnitude and direction of that, same piece, it's going to have the opposite direction, right, as we now are going this way. So I go negative 2i and down 11j. It's the same tangent value except in the other quadrant. So I would add pi to that value to flip that angle from here to that direction. Unit vector means a magnitude of 1. And the way we can get a unit vector is take the vector and divide all the components by the length. And so if I take this value, my magnitude of A is going to be 4 squared plus 5 squared, and we get a value. Our unit vector is going to take that magnitude and divide everything by that. So my I value, my I component, and my J component get divided by the total length. And then if I wanted to scale a vector, so a length of 8, I would take a unit vector, which has a length of 1, and multiply everything by 8, and that's going to be a vector that's 8 long in the direction of angle of vector A. So let's just say that we have this right here, right, which is 5 root 5. So if I wanted something to be 8 long, right, I would scale that unit vector by 8, and I get a vector in the same direction as that value. All right, we can put vectors into space. And space means 3 dimensions. So to put something in space, we add another component. We imagine taking the xy plane and flipping it down, folding it down, and extending the z-axis here. And these values now are called an ordered triple. So I have an x, a y, and a z value attached to any point that I've been given. And if I want to express that in terms of a vector, I have vector OP, which goes from the origin. That's called a position vector, again, because it starts at the origin. And I'm going to be able to express that in terms of I, j, and we need another unit vector to deal with the z direction. So my components now become my I value in the x direction, my j vector in the y direction, and my k vector in the z direction. And my components are simply xi plus yj plus z times k, whatever those values are. And for what we have specifically here, right, 2, 4, 3 will take the places of x, y, z. That's how far I actually go in that direction. We can do that with our pieces here. So again, x, y, and z, and we start to think about how those values would look. If I had some example, 2i, 3j, 4k, that would mean if I was to go out 2, I go over 3, and then I go up 4. It's hard to visualize on two-dimensional surface, but that would be my vector. And again, this is a two-dimensional representation of a 3D vector. Same idea, right, with these values, except I'm going back. Now I'm going to sketch as best I can. That's back 4 in the x direction, and then it's going to be back 2 in the y direction, and then up 3 in the z direction, and that's my resultant vector. That's the actual vector b. All right. And just like in 2 dimensions, we have 4 quadrants. If we divide this up, we have 8 octants for the 3-dimensional space. And our first octant is defined as where everything is positive. So positive x, positive y, and positive z would be popping out towards us from right there. All right. And again, these are hard to visualize. It's hard to draw. If you keep track of your components, you're going to be all right as we move forward. Okay. So again, let's look at this example. I go over 2, I go out 5 in the y direction, I go up 3. That's my vector A, right? That's that box. If I was to draw a box around it, it's actually popping out of the screen at me. And I have components attached to that. So my components here for this vector, as a position vector, again starting at the origin, are going to be simply those values, those ordered pairs. That's my start, the origin. I end at point A. And my coordinates are going to be something times I, something times j, something times k, and that's simply the scaled values of how far I went out in those values, which correspond to my coordinates. So it's simply 2, 5, and 3. That is my position vector in terms of components. We could add another vector. So let's say we have vector b, which is 5, negative 3, and 5. And that is going to be our displacement vector. That's our subtraction. And if we go in that direction, so that's the difference between them from our starting point to our end point, right? We'd have our start and our end, and we're going to subtract those values. So OB, that's our position vector. It's just, again, these components, right? And then to get that displacement vector, I'm going to subtract B minus A, which is going to be, in this case, those values. If I just look at subtracting this, I'll be left with those values there. Right? The magnitude might sound like it's scary. It's really just an extension of the Pythagorean theorem. So we take our components, right, and we square them, take the square root, and we get a value as we plug through it for our magnitude of that displacement vector.